Hello, this is Mrs. Myers, and we are going to talk about perpendicular and angle bisectors. A perpendicular bisector can be drawn for any given segment. On this segment, AC, we are going to draw the perpendicular bisector, assuming that point B is the midpoint of segment AC. So you draw the perpendicular bisector before I do. There's two words we need to know the meaning of, perpendicular and bisector. So bisector means it has to go through the middle. So we're going to mark the two segments, AB and BC, as congruent. And perpendicular means it has to be a right angle. So we're going to draw the perpendicular bisector going straight up. So that's at a 90-degree right angle there. So that's the perpendicular bisector. This second one here says draw the bisector that's not a perpendicular bisector. So this is just to remind you that not all bisectors have to be perpendicular. You could draw a bisector going through this midpoint, and that green segment there is a bisector. It's just not a perpendicular bisector. So there is a difference between bisector, perpendicular lines, and perpendicular bisectors, right? So there's three different things. In fact, this is perpendicular, right? But it's not a bisector. So perpendicular bisector just combines the two terms, perpendicular and bisector. Okay, equidistant, by definition, it's the same distance or the equal distance, equidistant, so same distance. So there's two theorems here. One is the theorem, the second one is the converse. This is called the perpendicular bisector theorem, and it just says that if you have a segment, AB in this case, and you draw the perpendicular bisector of it, draw this perpendicular bisector, then any point on that perpendicular bisector is going to be equidistant to the two endpoints. So if you draw this perpendicular bisector, any point, I could pick a point down here, or down here, or down here. Any point that's on the perpendicular bisector is going to be equidistant from the two endpoints of the segment. So basically you're just drawing the segment that every point on the segment is the same distance from the endpoints. It's like you could slide this point right down, keep sliding it down, it goes through the midpoint, right? Every single place that it is on this segment is going to be equidistant. So if you look at the if and the then here, if they're perpendicular and bisected, then basically if you draw the segments from any point to the endpoints, you're going to end up with an isosceles triangle. So this is really related to isosceles triangles, right? If you draw an isosceles triangle and you have a perpendicular bisector, all these things have to be true. It's perpendicular, it's bisecting the base, and the sides are the same. Okay, so equidistant. The converse is also true. If you have an isosceles triangle, in other words, if you have a point that is equidistant from the two endpoints of a segment, then that point would have to lie on the perpendicular bisector. It has to be perpendicular and bisecting the base. Okay? So, how does that translate into something that we can use? Well, if we have a diagram that looks like this, you have a triangle drawn here where you know that this segment BD, just by the markings on the diagram, I can tell that BD is the perpendicular bisector of AC. I can tell that from the markings on the diagram. Well, according to the theorem, if BD is the perpendicular bisector of AC, that means any point on BD is equidistant to A, same distance to A as it is to C. So point B itself is the same distance to A as it is to C. These are congruent sides. Therefore, 4x would equal 6x minus 10. So you can use this information of this theorem to help you draw write an equation and solve for x. And then you could find the lengths of these sides, right? If x is 5, 6 times 5 is 30, minus 10 is 20. 4 times 5 is 20. Okay, so that can help you find missing sides. The second problem here, you know what, let me just go back for a second. For those of you who are good at proofs, or need to be good at proofs, or want to be good at proofs, here's a challenge. You can write the proof of perpendicular bisector theorem. I'll give you a hint. Use congruent triangles like SSA and SSS and all, not SSA, that doesn't exist. SSS and ASA and all of those. Use congruent triangles. Remember, when you're writing a proof, the given is the if part, and the prove is the then part. So especially you guys in 21, you could try writing that proof. Okay, another example here, they're trying to give you a real life example here. There's an amusement park, and there's these two rides, the roller coaster and the spaceship chute, and this park wants to build a t-shirt stand that's the same exact distance to both of those rides. So the idea here is, if you want something, it doesn't have to be right at the midpoint. It could be. That could be a good place for a t-shirt stand. But this says it just has to be equidistant from both rides. It doesn't have to be right at the midpoint. It just has to be anywhere along the perpendicular bisector. So the idea is, if you create the perpendicular bisector, any spot on this perpendicular bisector is going to satisfy the condition that it's this equidistant to both rides. I could put it way out here, and it's the same distance to spaceship chute as it is to roller coaster. So if you're trying to find something that's equidistant to two things, it really can be anywhere on the perpendicular bisector. All right, this next one is a concept basically defining the word distance from a point to a line in geometry. What is the distance from a point to a line? If I draw an angle here, and I draw this line, and I put a point, and I say, what is the distance from point C to line AD? A lot of times people want to go straight down like this, like parallel to the side of their page. Everybody wants to just draw a straight line down. But really, the distance doesn't have to do with how your page is aligned. Let me change that diagram a little bit. Right? Now look, if I said the distance from this point to this line, if you go straight down your page, parallel to the side of your page like this, that's not giving you a good distance. That's what we sometimes want to do. We want to say, oh, let's just draw a line straight down. But that's not really how we're going to define distance. It doesn't have to do with how it's aligned on your page. If you think about your house, the front door of your house, this house here, and I say, what is the distance from this house to the road? You would probably measure from here to here? You would probably not say, oh, it's that far, right? You wouldn't really measure it in that direction. Even if I put my house like this, and the road here, how far is it from my front door to the road? This is how far it is. That's the distance you want to measure. You don't want to measure it going straight out your front door and down. That would be a really far distance, right? If you were going to try to put your mailbox on the road and you wanted the shortest distance possible, you'd put your mailbox here, right? So the distance is going to be defined as the perpendicular length to the line. So the distance from a point to a line is defined as the distance of the segment. I shouldn't say distance. We're defining distance, so let's not use the word distance. The length of a segment that is perpendicular to the line. It turns out that's also going to give you the shortest distance. Because we usually want the shortest distance anyway. All right? Okay, so in a figure like the one below, this is kind of getting back to that angle idea. To get the distance from this point to this ray, you don't want to go straight down like this. That's not the right distance. That's a distance, but it's not the distance how we defined it. You want the distance along the perpendicular. So think of the shortest distance from this point to the ray AC. And same thing here. You want the perpendicular. Okay, so there's a theorem that relates to this, the angle bisector theorem. It says that if you have the angle bisector, so in other words, this angle is getting cut into two congruent pieces here, two congruent angles. If you have QS as the perpendicular bisector of angle PQS, cutting this angle in half, then every point on this perpendicular bisector is equidistant to the sides of the angle. So it's the distance from the point on the perpendicular, the angle bisector. The distance from the point on the angle bisector to the sides of the angle is always going to be equidistant. So again, in a diagram, that is going to look like this. What is the length? What's the length of RM? So we have to solve for x. Well, if you know, this is marked as the angle bisector, right? The theorem said if it's on the angle bisector, so you have to check and see if it's the angle bisector. Then if it is, in this case it is, because they're marked congruent, then you know these two distances have to be the same. So 7x equals 2x plus 25. And then you could solve for x there. Okay, the converse of the angle bisector theorem is also true. In other words, if you have a point that's equidistant from two rays that form an angle, then it has to be the angle bisector. Okay, now look at these diagrams carefully and we're going to decide, is this A, this point A, on the angle bisector of angle TXR? So if we look at this first one, is A on the angle bisector of TXR? Well, we have to look at the clues. It says T to A is 8 and R to A is 9. Well, if that's true, then no. TA would have to equal RA. if A was on the angle bisector because of our theorem. So that one's going to be no. Number 30, is A on the angle bisector? Well, yeah, just by definition of angle bisector, this angle is getting cut in half. It's getting bisected, so it's marked that way. So yes, it's on the angle bisector. 31, we don't have a bisector drawn, but we do know that A is the same distance perpendicularly to the two edges, so yes, it would have to be on the angle bisector. Even though the bisector is not drawn, A would have to be on it when we draw it. Okay. I'd like you to try to do those problems in the book, just the evens. On the back, there's some review and practice from the previous lesson, 5.1, and there's some practice from 5.2 on this sheet as well. We will go over some of that in class tomorrow, and I'll give you the answers tomorrow in class for this homework assignment. So make sure you get that done. Okay, thank you.